Hey everyone, can you hear me?
Yes, we can hear.
Yes.
Okay, great. Okay, this one, US Central Time. We have to get it started. And thank you for coming. And this is a flash session. That means we have more speakers in 2 hours. And so I would appreciate if you can finish your presentation within 10 minutes. And then we will have some minutes for the transition and question and answers. And this is a session for AV, EV, SAVs, and transit. I'd say it's actually the same as disruptive mobility technologies. And we have 8 excellent speakers. And now I'm going to introduce the first speaker. Hold on, where is my cursor? Okay, first speaker, Mo.
Jun, you went on mute.
Oh, I'm sorry. Okay, anyway.
There you go.
Okay. Our first speaker is Mo, and his research falls in the integration of autonomous systems. And Mo completed his Master's of Architecture Engineering Environmental Design degree from Cairo University, and he holds a bachelor's degree from the university at this university as well. And his current research is utilize algorithms, energy simulation, kinematics, for the development of integrated optimization design tools for autonomous robots for city transportation applications and large infrastructure construction projects. All right, now, Mo, the floor is yours.
All right, thank you. May I share the screen, Jun?
Yes.
You've disabled participant screen sharing, so.
Zhong Ling is
yes,
our
yes.
room coordinator, and he's able to enable you to share screen.
All right.
Yes, I think you.
Oh, perfect. There you go. Thank you. Appreciate it. All right, everyone. Nice to see you virtually. And today I'm just going to talk about the Airspace Design and Management Protocol for Autonomous Unmanned Aerial Vehicle-Based Delivery in Cities. My name is Elsayed, and I'm speaking to you from McMaster University, which we acknowledge is sitting on the lands under the agreement of the Dish with One Spoon, One Palm agreement. And I acknowledge all the great efforts from my teammates at the Trip Lab and the Natural Resources Engineering Council of Canada for the grants that gives us the opportunity to do this research. So really quick today, I'm going to talk about a very quick introduction, and then I'll talk about the UAV systems, the airspace discretization, and then finally we'll talk about a little bit of conclusions and give the room for the Q&A. So as a very quick introduction, drones are causing this mass disruption in cities now, and it's equivalent to the disruption that happened when Ford came out with the Model T and there were no roads to drive on. So with all these investments and coping with the social and economic and environmental disruptions arising from the expansion and increased population density in our cities, we are having an increased demand for a parcel delivery, for a product delivery, for parts delivery. So this pushes further and further towards solutions like autonomous drones. The consumerization, as we can name it that way, of the civil airspace is very similar to this paradigm shift in cars. Now, the only difference is that when we had the ground and we designed roads, having those roads in the sky in the 3D is much more demanding and much more complex given the nature of cities, the safety requirements. So it poses a lot of challenges, and a lot of researchers have been talking about that. Lamerdell, Barr, Fiona et al. 2015. A lot of research out there is talking about how hard it is to manage this disruption, this revolution in drones. And these challenges are even harder for air traffic control systems. So we're talking here from a safety perspective rather than just the efficiency of the system. The fundamental idea here is that we need to provide a national framework for all the manned and unmanned vehicles in the same airspace because they share it. And given the traffic separation, the flight trajectories, using a single infrastructure here and with varying levels of sophistication. So what we're talking about here is designing roads in the sky. It's like a futuristic movie here. And NASA started this initiative because we really need it. We are in dire need to have this system in place. Now, UAV systems as a framework, this is what we've created here. We've created a framework or a protocol that allows every municipality or every design team to work on their own system and be able to design a fully autonomous air management system. Now, it starts with the user or the operator input and the air flight control authority. So then once we have the demand, we get the WebGIS or the city model archive and get the LiDAR data, 3D data of the city. So it's basically the model of the city. And then we create a dynamically updated 3D model with all the takeoff and landing locations. What you see on the left here is the LiDAR data set, and this is to an efficiency or to a precision of 50 centimeters. So this is the LiDAR data, the point cloud, and then we transform that into a 3D replica or a digital twin, as we call it, of the city. Now, once we have that, we can divide the air section into parts or parcels or layers. Once these layers are divided, like the picture on the right here, you can see how this becomes a segregation of the airspace system. Because the top layer is used by the bigger aircrafts, now the bottom layer is where we are utilizing our drones. Now, once that happens and you have the UAV operable airspace, you need to discretize it or basically divide it. So how can we divide that? We use a dynamic discretization method that we developed in-house. And there are basically, in this world, there are two ways to discretize an airspace. One type is the Cartesian method, which we can see on the right. So the Cartesian method is basically, or Cartesian, sometimes people call it that way, is a point cloud system. So it's a 3D lattice of points that you divide the airspace with. And then once you have it, you transform that into a graph problem. And this gives you the shortest path or the shortest trajectory for the drone. Now, on the left, you can see that there are other ways to discretize the airspace. And what we have done is that we have devised our own way in discretizing the airspace called SkyRoutes. And this algorithm, it basically builds on the segmental discretization of airspace. So it divides it into segments rather than points. Now, once we have the discretized airspace, the last part is creating an OD matrix, origin destination of the drones, to simulate or mimic all the missions that we're going to have in real life, and then the dispatch locations, the available UAVs, so that we allocate the tasks. Then once you do that, we have the final product, which is the routing based on the kinematics. So with that being said, the final part is that we have the discretized airspace and we have the routes of these drones for multiple missions. And what we do is that based on this simulation, we can create an exact replica of millions of missions in the sky in the realistic environment that replicates exactly what's happening in real life. And once we have the green light to actually do our experimentation, we update the LiDAR data, and this becomes the management or the air traffic control system. So as conclusion, the proposed framework provides a very robust, as you can see, air traffic management and planning method that is adjustable, and it's applicable to any dense urban center because you can just change the LiDAR data set, and then you have your own city, and you can even update the kinematic model of the drone so that you can change the type of the drone that you're simulating. Or in that case, if it's multiple types, a heterogeneous fleet, then you can change that as well, and you can update your system. The framework highlights that the airspace utilization gains due to the added airspace volumes with that framework is in the dynamic discretization method, hence adds more dedicated trajectories for UAVs. So basically, we're allowing more and more drones to fly in the sky. The benefits of using the LiDAR point cloud data as opposed to a very plain 2D method of course, that it gives you a realistic flight path rather than a suggested or a hypothetical flight path. Benefits of the dual keep in and keep out geofencing technique, which adds more layers of safety. The trajectories avoid the utilization of the space above urban blocks because we only create this space over roads. There is a significant order and coordination as compared to the traditional methods. The proposed framework for UAVs poses a significantly efficient airspace management system, making it fully autonomous UAV operations economically viable for last mile delivery within complex urban contexts. And that's it for me. I'll be happy to answer any questions. And this is my contacts and the QR code if you need to ask further questions.
Thank you, Moran. That's a great presentation, which is short and also informative. I appreciate that. We don't get questions in the chat box, but I do have a question about your presentation there. I mean, even though it said that the framework is proposed for the autonomous UAV, so do you think your framework would also be applicable or useful for the as a urban air mobility systems?
So the ones with a manned
flying cars, just transporting people.
Okay, so this is a really great question, Jun. So basically, because this framework is a protocol, it's not like a specific code where you can't change anything. Once you change the block that is responsible for the size of the drone, think about it this way: a small drone that delivers like the Amazon drone is just half a meter or like 60 centimeters or like a meter wide. Okay. Now, the one where Airbus is proposing to take customers is going to be wider. It's going to be larger. So once you switch this code, it becomes the bigger model. And once you do that, the trajectories that you design or simulate are going to accommodate this big drone that can transport human beings.
That's right. And also the dynamics of the demand is also quite different, because for those goods, I mean, maybe it's not very time sensitive, but for, I mean, our commuting travels, you think about that, it's going to be a lot of traffic in the morning peak hours.
Yeah, I mean, you have the dynamics changing here because our OD matrix was based on parcel demand, which, as you were saying, it's like a constant over the day. Maybe it spikes a little bit in the morning and in the afternoon. But when you're talking about something like an Uber drive, this is like a traffic jam in the afternoon. But then at the end of the day, it depends on the type of the city. So if we're simulating Sydney, if we're simulating Toronto, if you're simulating Los Angeles, it depends on the capacity of the sky in the city. If you have a lot of skyscrapers, you're doomed. It's done. You're not going to have a lot of customers to accommodate within the airspace. But if you have a low-rise kind of city like Oklahoma, maybe areas in like even Austin, Texas, not a lot of skyscrapers around the city, you can accommodate more and more of these bigger drones. So yeah, I guess so. It's and it can flex to avoid to allow the simulation of a heterogeneous fleet with different sizes.
Thank you. Thank you. I think that's great. And we don't have any other questions to ask. I mean, please allow me to move on to our next speaker. Our next speaker is going to be Dr. Monika Filipovska. She's an assistant professor from University of Connecticut, and she received her PhD from Northwestern and in 2021, and her research interests are in the areas about transport networks, traffic modeling with a focus on emerging vehicle and sensing technologies and data-driven predictive analytics. And she received the Research Excellence Award from the University of Connecticut in 2022 this year, and the Best Presentation Award at the 2020 IEEE International Conference on ITS. All right, Monika, now the time is yours.
Thank you. I will go ahead and share my slides. Please do let me know if you can hear me well.
Perfect.
Okay, great. So let me make sure I can see everything in one window. Okay, great. Yeah, so thank you very much for the introduction. Today I will talk about some work that is in relatively early stages. So I'm working on some traffic state forecasting with spatio-temporal network dependencies, and this particular approach uses a graph neural network to perform that task from some kind of transportation-driven perspective to incorporate the spatio-temporal network components. So traffic state prediction essentially is typically performed to predict the three macroscopic quantities of traffic, so the density, flow, or speed. And so it's typically also performed considering individual road sections. But as we all know, road sections are part of complex dynamic networks. And so the purpose of this work is to predict traffic across a network. So we want to know average traffic speeds over time across multiple locations to be able to see farther than the short term of 1 to 10 minutes, which is a typical prediction horizon in the literature with some exceptions, and to be able to not only predict over space, but also utilize those characteristics of the spatial and temporal impacts that we will learn through having the data observations throughout the network. So to give you a kind of more mathematical representation of this problem, we focus on traffic speed prediction here as a more user-centric measure of traffic as opposed to flow or density, and can be easily converted to travel times. We consider a given prediction horizon T and a set of observation locations throughout a network. And so then we are able to say that the speed is observed at any given time, forms a sort of vector of observations across all of these different locations. And those locations also can be placed on a network. So we use the underlying transportation network to consider all of the observation locations. So typically those would be sensors as the nodes of the network, and then use the underlying road network to build the connections between them. And so here then the goal is, given observations over a historical horizon at a time t, and given this representation of the networked locations, to find the speeds over a prediction horizon t. And this we would do by maximizing over some loss function or error function over a speed generating or data generating process that is also unknown. And so we need to build a model that aims to parameterize that process of generating, knowing the future speeds from the previously observed speeds. And so kind of more visually, the goal then is to collect data from stations across a transportation network. This typically would lead to thousands of sensors to measure that measure these average quantities observed with a given timestamp. And then the goal is to have a long-term traffic state prediction. And to do that, we typically need to capture both temporal patterns, spatial patterns, and sometimes spatial-temporal interactions in the network that produce these dynamics in the traffic state. So to give you an overview of the study that I will walk you through, essentially we first identify the study states and the study sites and the data that we use, how to extract these spatial-temporal features, develop a model architecture that aims to capture those important features, and then we test the model's performance. So I'll focus more on the experimental side today, just because that's where the most interesting parts come up. But in the data selection, we use a publicly available data set from the California Department of Transportation. So they collect 5-minute station data. They have thousands of stations. We select a particular district that contains the Los Angeles metropolitan area and its surroundings, and find around 2,400 active stations. So there are stations that don't actively observe data always. And we focus on a total of 12 months in the years of 2019 to 2021. And I will explain in the experiment design a little bit more how we use all of those 12 months. And then the network data comes from just the geospatial information of the road network, which we then match the sensors locations onto, and then construct the network connectivity or the station connectivity network. So what we want to then do is construct the observations of the speeds on the network for a given time stamp, and then have them observed over a period of time. So we get a sort of three-dimensional observation of the data. And then we want to do the same in terms of prediction, but for a prediction horizon. The model architecture that we use here utilizes several different types of neural networks. So it uses a graph attention convolution block first, which uses some attention mechanisms that aim to determine the relative importance of different features that are on the graph in prediction. And so we feed the locations and the connectivities of the stations, and also the weighted adjacency matrix, which measures the distances between them. And then the attention mechanism is able to use that information and sort of weigh which locations give most information about the locations that we care about. And then the convolutional network block is able to capture patterns over space and time. And so this is also necessary because once we compile these observations over time, they form a time series. And then we lead into a fully connected output layer to get the same type of formatted output that we need of observations over space and time. And so in the experiment design, we use a historical horizon of about 60 minutes and then a prediction horizon that varies from 20, 40, and 60 minutes in order to evaluate the performance of these throughout different prediction horizons. We create one training scenario that uses data from May and June in 2019. And then again, this is separated into a training and testing batch. And then we create 5 different testing scenarios that use data from different time periods. So there could be a variety of things that could change in the traffic patterns over these time periods. So some are in the same year, just a little bit later and in different seasons. Others occur after or during the peaks of the pandemic, and then as we recover from the pandemic. And then we use 2 comparison approaches. So a simple convolutional neural network, which captures spatial patterns by itself, and then a long short-term memory network, which is used for time series prediction and can capture temporal patterns. And so we use these to compare with the proposed approach. So in these results, I will show you 3 figures in which we have the performance of the proposed approach here labeled GAT-CNN with the green color, then the convolution neural network approach in blue, and then the LSTM approach in gray. And then for each of these, I'm showing the mean absolute percentage error in prediction for the 3 horizons, the 20-minute, 40-minute, and then 60-minute prediction horizon. And then the scenarios that you see on the bottom are the training scenario first, labeled TS0, and then the 5 testing scenarios, 1 through 5. So there are a lot of observations that can be made here. I will kind of draw out the most important ones, or the most immediate ones, let's say. So we can see, first of all, that as the prediction horizon increases, the errors increase. This is expected. It's harder to predict for the longer term. And this is kind of translates for each scenario, or for each testing scenario. The proposed approach seems to show some consistency of outperforming the alternatives. So it is always has the lowest error, while the alternatives between them one another sometimes compete. So sometimes the CNN performs better, while at other times the LSTM performs better. And that lack of consistency can be really deterrent from using those approaches. We see that the proposed model performs well in unseen cases, but there is some significant variation between the testing scenarios. So testing scenarios 1 and 2 seem to have higher errors in all cases, while testing scenarios 3 and 4 have relatively low errors in all prediction horizons. And this is definitely something that we need to look into further, what type of changes really occur that lead to this difficulty in predicting them. So I will kind of conclude with some key takeaways, but I would like to discuss more if we have time. So the proposed model we saw can find spatial-temporal features into traffic data. We are able to predict with a longer prediction horizon, so 60 minutes is relatively high. And we see consistency in performance and in transferability, which is quite important, especially when we want to train and then use this model for years. In future work, we would like to test potentially on different network sizes and see if there's any improvements or changes in performance, test with different historical and prediction horizons, help in making the model more efficient, and also learn how to interpret the changes between these scenarios that we tested and other new testing scenarios to understand what type of traffic dynamics really impact the performance of the model and how often do they need to be retrained in order to be useful. So that's all I had for you today. Thank you. And I would be happy to take any questions, or if you would like to discuss offline, I've also put a shortened version of my email down below.
And we have a question from Professor Kockelman. Do you have a link to your paper?
So this work is not published yet. It has not even been submitted for publication. So unfortunately not yet, but I could follow up with you. Probably it would take about a year to be out. So
I'll just say, June, that I recommend that you put your preprints up when you feel good about them. So a lot of us submitted papers this week by Monday, I guess, to TRB, and so I always put all my papers up there, and I highly recommend it. I don't know if people are scared that somebody's going to steal their ideas, but I've never seen it happen in my case. I've got 200 publications, and I've never noticed this happen, so I really hope you guys aren't too worried about that. Yeah, that's a great idea.
I just haven't not gotten into the habit of it, but and especially because this work we haven't even written up yet. So, but once we get to that stage, it would be great.
Okay, so you submitted just an abstract for this session.
That's
okay,
correct.
got it.
Yes.
Sorry. Yeah, there's probably not a paper quite there yet. But yeah, I do make that as a general recommendation, especially to all you young faculty. Your work's going to be found through the Google sniffing trail, and you're going to get a lot more citations that way. And all you do with your preprint, it's not the final paper because that's not legal to post that, but the preprint can say where it was ultimately published. So when people go to that same link later, they'll see and they'll be able to reference it as a proper publication at that point as well. So you shouldn't hesitate to do that. I think it's a great option for all of you with web pages.
Great, thank you for the suggestion. I appreciate that.
All right, Monika, we have a question from Connor. Is there anything unique about LA that might be driving this research? And LA is quite terrible for traffic because we have learned all the statistics from LA about congestions.
Right. So in this particular case, we use the LA because of the free and abundant data. So Caltrans collects data from across the board of California. So that was publicly available, and LA seemed like this particular district was a good combination of urban traffic and then also having a lot of freeway and highways, which are the locations that have good stream of data throughout time. And so the difficulty that I encountered with actually using that freely available data is that there would be intermittently missing data from various sensors that you couldn't use a continuous observations throughout time. And so that was one good thing about the LA area because of those specific highway and freeway networks.
Yeah, if Jun will allow me to follow up, I just wonder if it's because, for instance, LA is consistently terrible, as he mentioned. It's just always backed up or whatever it may be, where a more medium-sized city, I could imagine like a Minneapolis or something, maybe has actually more variation because it's not as bad. And so maybe that makes it harder to predict. And I wonder if you just have like any thoughts on that.
It's true. I have not thought about that much. We do have some, I didn't,
that's actually something I want to ask is about, because the traffic patterns can be recurring and non-recurring. I mean, I'm not sure what you're predicting. You're predicting recurring patterns or non-recurring patterns, because those incidents or crashes are definitely going to affect those states.
Yes. So in this particular case, we try to just predict, we feed the information of our past observed period, which may or may not contain incidents, and then again predict over a period which may or may not contain accidents. I think in that case, when thinking about it for non-recurring events, it might be interesting to find whether there is a particularly suitable subset of data that actually contains the types of situations that might occur or kind of captures them better. Because really the limitation here is the predictions only depend on what the model has seen before, right? So if there are cases that occur that have never been seen in the training, they're much more difficult to capture or to really be correct in prediction. And so I agree with that. I think the work lies in figuring out what is the correct training set and what it exactly needs to capture.
All right. I mean, the last question for Monika is I'm curious which attention mechanism you used in a GNN model, and do you think this GNN model can be applied to other time prediction?
So I'm not sure about applying it to time prediction tasks in particular, because the key here was that we had the underlying graph. And so the attention mechanism is applied onto the nodes of the graph, or essentially the links of the graph. And so it weighs the links of the graph, yes, in a self-attention manner, but the links in the graph essentially capture what is the relatedness between the different stations, and so how to use that information of neighboring stations. So applying it to time prediction tasks, potentially yes, if there's a way to build a graph on it, right? Because the input does require a graph.
All right, thank you. Thank you,
Thank you
Monika.
very much.
That was a great presentation. And let me move on to our next speaker. Our next speaker will be Gyugeun. I'm not sure. I think I'm not making a correct pronunciation. He is a PhD student at NYU, New York University, and he received his bachelor's degree, master's degree from Seoul National University, and his dissertation topic is route design with optimal learning. His research interests include urban mobility, route planning, simulation, and optimal learning. All right, Yoon, now it's yours. Time is yours.
Thank you so much. I will share my screen with you all. I hope you guys can see this. Okay.
Yes, thank you.
All right. So thank you for being in this session. My present subject is the simulation sandbox to compare 3 different transit operation types. And it's quite different from my dissertation topic, but we have this project in the one project supported by Federal Transit Administration, in short, the FTA. We have one technical report, and it is the one of the most primary source of the most contents in this presentation. We also have the recorded video to explain how to use the simulation, and also we have the published paper regarding this one. So the primary objective of this simulation is to bring the real situation to the virtual environment and run what kind of things will happen if we change this and if we change that. So in reality, we can observe many things change. For example, demand changes, and also other technologies can be adapted to existing transit services. So many elements are not constant, they changes every time. So practitioners should evaluate those transit systems not based on the actual physical system, because it's very costly and it's very time-consuming work. Instead, they can take a detour by using the simulations. But usually some commercial simulations are expensive for those, and so they may want to use some open source simulations if they're available. And we try to specialize the simulation with very simple code, and this is also open to public. So if you are interested to look into it, then you can use it. I will explain it further in the next slides. So the main objective is for the practitioners who wants to evaluate their current systems and who wants to evaluate some alternatives compared to their existing ones. So there are several elements in transit systems, such as routes, stops, vehicles, and timetables. They can vary, so they can be flexible. So in this classification, there are 2 extremes. One is a fixed route. So most of the elements are fixed. They are expectable, and they remain constant during this significant time. Meanwhile, the on-demand microtransit system, everything is flexible. Routes are generated dynamically, and there is no fixed stops. They generate stops if there's a demand, a pickup or drop is requested, and vehicles can be various types, and also so the time there's no time to on dynamic transit. In regard instead of these two extremes, there is also the intermediate version, which we can call flexible route system. And in the graphical description, we can show how these are different. In the fixed route system, there is a mid baseline, which is fixed route, and vehicles only travel along those routes. And small triangles, which are passengers, access those stops, circle, and squares. And they are the service region is determined by the walking distance from the distance limit from the route. Meanwhile, the flexible route also has the fixed route in the middle of the service area, but it has fewer stops which should be visited by vehicles. Instead, between those stops, vehicles can deviate freely and they can serve the passengers. Passengers can take two actions. First, they can wait vehicles at their original locations, or they can access those fixed checkpoints. On the other hand, on the Microtransit, there's no fixed route, and vehicles can freely navigate all within the service region. So in the simulation, we accept three different kinds of information. First is passenger information, the second one is vehicle information, and the other one is the last one is a given environment. Passenger information is it's related to the request, the origin, destination, and request time. For vehicle, it's a specification of the vehicle, such as capacity, average speed, and for given environment, it's a geographical aspects of the network, such as the size of the service region or how the route looks like. So the simulation first identifies passengers of who is requesting their services, who is already inside the system, and combining all the information together, the simulation can build a candidate routes which can be chosen based on the value of each route. And after finding the best option, then we can update the information by actually moving passengers and vehicles within the simulation. Then for each time step, we can track down the location of the passengers and vehicles. And based on the changed, updated information, we can re-identify passengers at the next time step, and the simulation goes on. And this simulation is written in MATLAB, but we have planned to translate this code into Python to increase the accessibility to this code. So here is a very simplified input and output of the simulations. And we can look into outputs, which is classified into passenger, vehicle, and system performance. For the passenger information, we can track when the passenger boarded or alighted, and when they arrive at the final destination, and how long they waited, how long they traveled in vehicle, and so on. For vehicles, we can track their trajectories and load profile and how long they ran within the service, and who just used that vehicle. And the most important thing is the system performance. We can also extract some meaningful information, such as the average wait time, average in-vehicle time, or the total vehicle mileage and ridership as well. We conducted a case study in Brooklyn, in New York, with the bus route called numbered B63. We input some facts collected from the online resources and ran the simulation based on 15 different cases. So since there are 5 different system designs, there are 3 classes of the operation types, but fixed route and flexible route, they have 2 different designs. So in total, there are 5. And scenarios, we vary different demand levels. So 80, 200, and 400 passengers per hour are assumed to be arrived in the service region. And here is the sample of the vehicle trajectory. You can see the fixed route transit, which is green line, just travels along the green middle of the service region, while the fixed flexible route transit visits these yellow diamonds, and while deviating freely between those checkpoints. And on the microtransit, definitely it just have no restriction of traveling all of the service region. We can implement this trajectory to the GIS map, but it's not automatic process. We did it manually to show how in reality the vehicle trajectory would be. And this is a summarized ridership. As the passenger arrival rate goes higher, then the number of the total ridership increases, but it depends on what kind of system you're operating. So for example, the door-to-door service, which is on-demand microtransit, it's the increasing rate of this most flexible system is much smaller than others because of the inefficiency of the system itself. And the weighted travel time, is the shortest for the on-demand transit because it is most personalized one. And the total vehicle mile travel, definitely the on-demand transit travels the most distance compared to the fixed route or the fixed route or flexible route, especially for the optimized fixed route shows the shortest vehicle miles travel because it optimizes the frequency itself, which means the number of vehicles operated is smaller, fewer than the existing scenario, so it could save more operational costs than others. So here, I think it's the end of the slide, and if there's any questions, I can listen from you. Thanks.
Thank you. Thank you for the presentation. And we don't have questions from the chat box right now, but I typed the question there because it's called microtransit in this in your research. I'm just curious how that is different from the paratransit.
Yeah, so it's very controversial how to define the microtransit and the paratransit. So I think in general, microtransit is paratransit including the microtransit, but microtransit itself can also include some transit which has a very small magnitude, such as using very small vehicles but operating on a fixed route. But the paratransit, they may not have some fixed routes, and in most cases paratransit should be reserved in advance of their trips. So if we call the on-demand microtransit, then it will share the most features. But if we compare the microtransit and paratransit, then there can be gaps between some microtransit services which operates on the fixed route.
All right. Yeah. I mean, I feel like there's just so much overlap there, and microtransit, paratransit, and also ride sharing, ride hailing services.
Yeah.
It feels like, I mean, they are all kind of serving the mobility, the travelers, I mean, without the fixed routes, and also they can request a service anytime. I mean, as long as the service is provided at that time. So that's just my understanding. I know there's, overlap there. And it's great. But I mean, now, I mean, my next question would be, it's like, I mean, why? Because you have shown a bunch of performances than, I mean, the vehicle miles, and just a lot of vehicle miles, a lot of more vehicle miles with the microtransit. And I just want to say, what are the kind of the benefits we are getting for the agencies, and also benefit? Well, it's very clear benefits for the travelers, but the benefits for the agencies.
So you mean what will be the benefit of the agencies if they operate the microtransit?
Operators, yes.
Yeah. I think with these measures, I cannot say there's no benefit for the operator side, but there can be a chance to prioritize the services because that part is very similar to the private mobility services such as Uber or Lyft. So it's also happening because VI is taking over the many mobility markets in United cities. So I think shaping the market in very similar to the private market could be the benefit of the agencies, just reforming their profit structure by excluding that.
Yeah, probably. Yeah, you're right. I mean, probably maybe it's, there's so much indirect benefits of that. I mean, to make those areas more livable, and then more people will move in there. They can generate taxi and more revenue there. So yeah, I think that's great. Okay, all right. I mean, now it's time to move on to the next. I mean, thank you for your presentation. It was really great. Let's move on to the next one. Our next speaker will be Phillip, who received his bachelor's degree in civil engineering from University of Campbellton in March 2020, and he worked in Uganda in engineering consultants for 12 months before joining Dr. Kockelman's research group for his master's degree in January 2022, this year. And his current research interest is travel demand modeling and shared autonomous vehicle fleet operation simulation. All right, I mean, Phillip, are you here? Yes, I saw you.
That's right, I'm here.
All right, great. The
Let
floor
me
is
share my
yours.
screen now.
Yes.
Thank you. Okay. So yeah, my name is Philip Ayebare, and I will be speaking on SAV operations across distinct Dallas-Fort Worth geofences. So as a bit of a background, based on previous literature, we have seen that autonomous vehicles are tested publicly now and boast potential benefits in household vehicle ownership and congestion. And the AV technology is likely to be operated at a substantially lower cost, and that SAV operations are expected to be affordable at between $0.50 to $1 per mile with profit, and also that user perception is continually evolving with respect to sharing vehicles and sharing rides. And so because of that, we are extending SAV operations to the Dallas-Fort Worth area. So we're using the Polaris framework to simulate shared autonomous vehicle operations. And so firstly is that the Polaris framework is an agent-based modeling framework that's designed to simulate large-scale transportation systems. And this includes travel demand, network.
Oh.
So he is in Uganda.
Yeah, sorry. I think I lost you guys for a minute.
Yeah,
I think I
we
lost
did
you guys
lose you. Did you want to go ahead and email me your slides in case we lose you again?
Yeah, of course. I thought I submitted my slides and my recording. So not so sure if you guys came across
I think
them.
Donlin, you have Philip's slides, right?
Yes.
I did submit my slides and my recording.
Just in case we need it, I mean, please.
Just in case we need it, yeah.
Yeah.
But I think I can share my screen again and keep on. So
okay.
It's all right. Yeah, from where I had stopped. So yeah, I was saying that I was talking about the Polaris framework that we used to simulate SAV operations. And I was saying that this Polaris framework, because it boasts short computational times over 24 hours, it could simulate all of DFW 7.5 million people. And in context, 25% of DFW's 25 million trips were simulated in about 3 hours. So this SAV module in the Polaris framework mainly contains revolved around the operator and the SAV vehicle. And then there was SAV agents that were developed to model the operations of the SAV fleets, right? So the SAV operator basically receives trip requests from traveler agents and assigns the nearest idle vehicle to pick up travelers and suggests repositioning for vehicles that have been idled for long periods of times. And then the SAV vehicle executes pickup, drop-off, and repositioning tasks depending on the instruction received from the operator. So the vehicle will store requests that are being executed and those that need to be executed in the future. So the DFW case study, this area that we are researching on, contains 42,000 links, over 42,000 links, 28,000 nodes, and 5,000 traffic analysis zones. While some other important facts include the 12 counties and the 10,000 square miles and the 7.5 million residents, and over maybe 3 person trips per person per day and 7-mile average trip distances. And so SAV operations in the geofence service areas were investigated under 3 different geofences with and without dynamic ride sharing. The region's population was sampled at 25% and used to calibrate the travel demand for the region. So the fleet sizes that we tested here included 1 SAV for every 10, 50, 100, and 200 residents in each geofence that was investigated, and mode choice alternative specific constants were scaled up to depict a 7% SAV mode share. So here we have our 3 SAV geofences. So the first geofence includes the entire region geofence that contains all the 12 counties, and then the next geofence scenario includes the 4-county geofence that serves SAVs in Dallas, Tarrant, Denton, and Colin. And then the next scenario contains the 4-city geofences for the 4 cities of Dallas, Fort Worth, Denton, and Plano. So these are just colored differently now for the sake of identifying each of them, but the county is one scenario and the cities is also one scenario. These are not different scenarios. So we got some results from some simulations. We saw some effects on VMT, both total and empty vehicle miles traveled. We saw a 1.05% drop in regional VMT when using the 4-city geofence versus the no DRS scenario in the best case. And all this was while serving 25% of all trips in the region. Then we also saw that DRS was effective at lowering the system VMT, but only when SAVs had reasonable market share. The market share of SAVs in our case was at about 5%, and so anything that fell below 3% did not really depict the effectiveness of DRS. So SAV fleet empty vehicle miles traveled also rose from 16% in the full region scenario to 20 and 23% in the 4-county and the 4-city scenarios. This came about as this was definitely unusual, and we could look at it as a limitation. This unlikely increase in EVMT from the 12-county geofence to the smaller geofences as the area of operation shrunk was unusual and unlikely. This could be because we didn't cover all demand in the region, while assuming that the same fleet size for all the geofence areas. Alternatively, we could change the mode choice alternative specific constant parameters to make this a much more used service, and so that we could make much more use of the fleet. And so these are just graphs depicting what I was just talking about, the decrease in total system VMT, right from the no DRS in the no fence scenario. Okay, the no fence is the 12-county geofence, yeah, without the fences at the county and the city level. And so yeah, we saw a 1.05% decrease. And then we also saw the unusual, the unlikely increase in empty vehicle miles traveled as the area of operation shrunk into the county and the city. So for the next studies, this will definitely be modified, and these results will probably make more sense. And then we also investigated SAV VMT and idle time. We saw that there was a 1% decline in VMT for larger fleets and a 10% increment in VMT for smaller fleets as the area of operation shrunk from the county level to the city level. So the daily average daily SAV VMT reduced by 53% for smaller fleets and by 45% for larger fleets, with as the area of operation shrunk from the 12 county to the county and then to the city level. And then idle time also increased by 6% from the best case, which was a 12 county case, to the county case, the county fence, but it remained relatively constant from the county to the city level. So yeah, this is depicting as well what I just mentioned about. We can see that this graph over here depicts the idle time, and you can see that there was a sharp increase in idle time as we moved from the 12 county fence to the county fence. The smaller county fence as the area of operation shrunk, and then there was a relatively constant idle time from the county to the city. So also we looked at the wait time and the average vehicle occupancy. We saw that AVO values are higher in the best case compared to the other two geofence scenarios. We also saw that average passenger wait times increased by 3.5 minutes across the largest, the smallest fleets in the best case with DRS, and then this increase was even higher at 6 minutes without DRS. So we see here that the geofencing at the lower level, at the county and the city levels, is going to lower these differences in wait times between the fleet, the largest and the smallest fleet sizes, to under 2 minutes, regardless of DRS. So in conclusion, we just saw that the smaller geofences had slightly higher EVMT and idle times, a bit unusual, but shorter wait times, and then AVO gains were larger in the best case with lower trip density, and the small decline was observed in the geofence scenarios with a shrinking area. And then we saw that it could be because of our fleet sizing and also maximizing demand that some of our results may not yet be as accurate as expected. But of course, it's just a work in progress, and so with time and running more simulations, we'll probably definitely get the right values for this. So future research directions could include multiple operators, managing fleets concurrently with different pricing strategies in a competitive environment, analogous to TNCs like Uber and Lyft and the likes. Yeah, so that concludes my presentation. Any questions, comments, and suggestions will be welcome. Thank you.
Thank you, Philip. And we have a question from Connor. He said, I think it'd be interesting to compare the welfare trade-offs between EVMT idle times and waiting times to identify what the socially optimal policy would advocate.
Come again? Oh, I didn't hear your question.
Oh,
You might want to read it in the chat box, Philip. But
okay, all right, sure.
Yeah, it's too bad Murthy's not in the room with us, because Murthy knows the choice equation pretty well. But yeah, we do have equations that help with the endogenous demand trading off certain things. But empty vehicle miles traveled, is not usually something that the users care about. And so Matt Dean, I think, does have some objective functions where he's trying to put all three of those things together because they're coming from different sources. So it's kind of a social welfare calculation.
So did Dr. K answer the question?
Oh, yes, absolutely.
Okay.
Sorry. Thank you so much.
Right, sure. Thank you.
Do you have any other questions? We have 3 more minutes.
I do want to mention that Philip is in Uganda right now. So he was here last week, but then he flew all the way over to Uganda. So I think he's in Lagos or Laos. Is that how?
No. I'm in Kampala. Right now.
Okay.
That's in Nigeria. But yeah.
Oh my gosh.
Oh, so far, yes. But I'm in Kampala right now. I'm so sorry about the Wi-Fi, but I made it.
Oh, it was great. It was great.
Yeah.
It was great.
Okay. Sure. Thanks for listening in.
So he just started in January, so he had to get running. And so Gurumurthy was mentoring him quite a lot for this work. And of course, we had to get all the models together for Dallas Fort Worth. So we're still tweaking, I think, the models quite a bit.
That's great work.
Thank you.
Okay. All right, if you don't get any, we have one more question. Can you please share the link to your paper? I think Dr. Kockelman can.
Oh yeah, sure. I think it's on Dr. Kockelman's website. It will be
Well,
in the next
no,
few days,
yeah,
or I don't
it's
know.
not in great shape because remember,
not in
he
great shape
just
yet.
started in January as a master's student, but it will be at the website I put in the chat box within a week. But again, it's a real draft version, so we'll try to update it as soon as we can. These were just submitted as abstracts. This is a flash session, I think. So.
All right. Okay. With that, I mean, let me move on to our next speaker, Connor. Connor Fassi is a PhD student, mechanical engineering from SMU, and his research focuses on intersection of policy and personal transportation. And he is advised by Jeremy Michalek and Kat Whitefoot, who are both professors of mechanical engineering as well as engineering public policy at SMU. All right, Connor, now it's yours.
Alrighty, thanks so much, June. I appreciate you. Yeah, so I'm Connor. This is going to be some work that I've been working on with Ken Gillingham out of Yale, and then Jeremy and Kate, as June mentioned, are my advisors, both of them from CMU. And it's going to be on what's driving electric vehicle adoption, what's changing over time that's changing purchase behaviors in US battery electric vehicle adoption. So to begin, the adoption of future battery electric vehicles is particularly uncertain. It's low right now, but it's been growing quite a bit with the Model 3 coming on the scene and so on and so forth. But the recent National Academy's report about personal transportation efficiency identifies adoption as one of the most uncertain aspects of this transition. And so we're curious about why consumer purchase behaviors have been changing over time. And so what we're going to do is we're going to compare consumer preferences over time for battery electric vehicles. We're going to compare the technology implications over time as they've changed. And what we do is we provide evidence that consumer purchasing behavior is changing because of technology rather than changes in consumer preferences over time. So what we do is we replicate a survey from Helvesen et al. 2015, where they were looking at consumer preferences for battery electric vehicles. Here is an example question from there. It's a stated choice survey where they're given a set of hypothetical vehicles that vary across several attributes, one of which is BEV powertrains, battery electric vehicle powertrains. We update that survey with some new values to better represent the current vehicle market. And then we've collected data on the order of 700 car buyers and 800 SUV buyers. So before I get into the results and the comparisons, I just want to talk a moment about willingness to pay so we're all on the same page. When I say willingness to pay, that is the value difference between two alternatives that are identical in every way except one. There's one attribute difference between the two alternatives. And so, for example, we could consider two vehicles, these two, that are both gasoline vehicles, and they look identical, and they also are both American and drive from, or accelerate from 0 to 60 in 8 seconds, et cetera, et cetera, et cetera. They're identical, except for one of which, the leftmost vehicle, operates at 1 cent per mile more expensive than the other. If we were to say the willingness to pay for that is negative $2,000, and the rightmost vehicle is priced at $22,000, then in order for the average individual to be ambivalent or to be 50-50 on which one they would choose, we would price the leftmost vehicle at $2,000 less to account for the loss in value that that increased operating costs incurs. So that's willingness to pay. And we directly measure willingness to pay using a mixed logit model in willingness to pay space, where we've assumed all willingness to pay coefficients are independently and normally distributed. Now, here's our overall equation, and I can talk about it in more detail if you all have any questions. But what I want to focus on is that we have an indicator for every BEV powertrain, not for every BEV powertrain individually, sorry, but an indicator for BEV powertrains. And then we allow the willingness to pay to scale linearly with its all-electric range for battery electric vehicles. And so there is a value associated with being a BEV and then its relative range. So we can talk about these other things later if need be, but I'd also like to mention that we don't just replicate Helveston's study. We use their data that they collected, re-estimate it using an improved estimation technique, and then compare those updated results that are based on their data with our results from our data. So the big takeaway is that we weren't able to identify any differences over time in terms of willingness to pay for BEVs. So we compare the means and the distributions of all shared model attributes, so BEV indicator and BEV range. We compare those over time and we find no statistically significant differences in mean or standard deviations for our parameter estimates. Here I've plotted the mean willingness to pay for a battery electric vehicle of a given range without any BEV fast charging as a function of range. And you see in the blue line, that's the estimates from the 2015 study data. The orange line is our updated estimates from the 2021 study data. And you can see in the overlapping range, those are statistically unidentifiably different. So we're not seeing any differences in car buyers. This is for car buyers. But we do see that as the range ticks up to 300 to 400, all else being equal, individuals on average are starting to value battery electric vehicles comparably to their conventional vehicle counterparts. We do this for SUV buyers as well. The story stays largely the same. We see there's no statistically identifiable difference in the shared ranges and the coefficients don't change. And as we get to higher ranges, we're approaching that conventional vehicle value as it gets closer. So overall, most coefficients can't be identified as different over time. And all alternative fuel powertrains that we estimate can't be identified as being different over time. And only amongst car buyers are there some coefficients that are changing, but they're not particularly relevant to the average BEV. So what we do is then we look at technology changes over time. And the technology has changed over time, at least for the small subset of vehicles that were available throughout the entirety of these studies. So we collect historical specification and current specification data for a few head-to-head comparisons of vehicles that come in both battery electric vehicle versions and conventional or gas-powered vehicle versions. And then we combine that with some projections from the National Academy's report that I cited earlier. And we estimate that overall willingness to pay, comparing these two head-to-head models, or head-to-head vehicles, incorporating all of our measured coefficients like acceleration and operating cost. And so we can look to the Nissan Leaf and the Nissan Versa. And the Nissan Leaf has been available since before 2013, though I did hear a rumor that they're going to stop making them soon. And what we can see is that the value in blue here is increasing over time. This is largely driven by range and some improvements in acceleration, but very small, largely range, all while the price premium of the set head-to-head, so in 2013, it was almost $20,000 more expensive to purchase a Nissan Leaf over a Nissan Versa, is going down. So price premiums are going down, and it's expected that the range is going to keep increasing, which is increasing the value of that BEV relative to its gas-powered counterpart, and so much so that it actually exceeds the price premium, at least in this example. And we can do the same thing for SUVs, though there's been no SUV that's been on the market the same length of time as the Nissan Leaf. But Hyundai has the Kona, which is available in both EVs and conventional vehicles, and it sees a similar sort of expectation in terms of price premium decrease and increasing range, increasing its value. So that was looking at some head-to-heads. When we performed an exercise where we considered a future scenario where there is just more BEVs on the market and there's more, and so there's more availability. So we take model year 2020 data from the most recent CAFE analysis, and then we estimate the share of BEVs that are available on a market-wide basis when every gas-powered vehicle has a hypothetical BEV option associated with it, just to get an idea of what a future scenario could look like. And with expanded availability and tech increases over time, we'll see more BEV adoption. Here I have the share of new cars that would be sold, or that would be BEVs in the model year 2020 compared against the current, or the model year 2020 actual share. And in 2020, even with a higher price premium and lower range, we see huge improvements. But in 2030, where we assume an equal price premium to a conventional vehicle and a 300-mile range for these vehicles, we would see over a majority of car buyers owning BEVs. And for SUVs, the story is similar. We see huge improvements in model year 2020, near majority status in 2030. And so in conclusion, future's looking positive for BEV adoption. We've replicated an earlier survey, fielded that survey, and collected 1,500 respondents. We found very few identifiable differences in consumer willingness to pay over time, and none for alternative fuel vehicles. But future projections suggest that BEV value is going to increase over the next decade, largely due to technological improvements that are predicted for them. And that's all I have for you guys. Thank you so much.
All right, thank you, Connor. Thank you for the presentation. And we have a couple of questions in the chat box. Do you mind reading?
Yeah, so for Kara, so 400-mile range absolutely is a lot. Most of what we predict here, so the National Academy's report predicts a 300-mile range by 2030 as having the same average price as a conventional vehicle. That's just that's what they expect for battery prices to decline. And so that there's a lot of uncertainty there. We don't project battery prices ourselves, but that's their projection. And then let me read through your second comment. I am not familiar with the new bill yet, so I could not attest to the change.
Thanks, Connor. Take a look at it and maybe email me. I'd love to hear your thoughts.
Yeah, absolutely. I will try to do that as soon as I can. And so for Kai's question, in the willingness to pay equation, do you consider the makeup price from the, or assuming markup price from the dealer due to the recent chip constraint? So all of this is devoid, well, it's not devoid, let me say, it's not with respect to the market that we necessarily see today. Some of it is informed by that, but what we give the individuals is we give them a price and we say that is the price of the vehicle, and then they have to choose, well, would you choose that vehicle? And so we can account for that by altering the price of our BEVs that we are simulating things for, but we do not specifically account for the chip shortage that is occurring in this moment.
Thank you, Connor. Thank you.
Great. And I'll. So in this, we do not account for incentives. So this is sort of, if BEV incentives were to continue along, say for these scenarios where we account for market-wide impacts, the assumption is that by 2030, actually, they're going to be the same price as gasoline vehicles. And so incentives wouldn't even be necessary, as here they would still account for, or they would account for more than 50% of the vehicles. And then so far as my head-to-heads that I showed earlier, I am not accounting for those incentives as well. So these are the raw price differentials pre-incentives here. And so if the incentive were to continue, you would see that the BEV value is actually, or if you were to allow for the incentive and you were able to claim the full incentive, you would see the BEV value is actually really close, especially in the 2020 case, to the price that one would net out, if that makes sense.
All right, thank you, Connor. If we don't have any more questions, I'd like to move on to our next speaker. Is Dong Zhao here?
I haven't seen him.
All right, that's fine. We are. Let's just move on to our next speaker. Our next speaker, who is actually the organizer of this conference, Dr. Hawkins from University of Nebraska-Lincoln, and he has a PhD degree from the University of Toronto and a master's degree and bachelor's degree from University of Calgary. And he completed his recently completed his postdoctoral work with Dr. Professor Kockelman at University of Austin, and his research is more about analysis of sustainable infrastructure systems and through application of a wide range of analytic tools. All right, Jason, you ready?
Yeah, I'm ready.
All right.
Thanks for the introduction. Sorry, I didn't send you the details as the organizer. It's bad on me not taking my own advice. Let me just see here. Let me get a. Where is that? Let me go back to the beginning of my presentation. So this actually pivots quite nicely off of what Connor was talking about in the last presentation. So this is very initial work that I've been doing with my master's student and then 2 undergraduate assistants during this past semester. And what we're looking at here is this question of the relationship between charging stations and electric vehicle adoption. And this is one of these, what they call a chicken and egg problem. They're calling this the electric chicken and egg problem. And a lot of my slides here are going to be fairly visual. If you have any questions about any of the technical details of it, I'd be happy to answer them. So as I said, the question that I'm trying to answer here is what comes first, charging stations or electric vehicle adoption? And this is a very important question, especially with the Biden administration looking at rolling out 500,000 plus charging stations across the country. Is what relationship or what is sort of the causal relationship between charging stations and electric vehicle adoption? Which of them comes first? What's sort of the strength of that relationship between these 2 variables? And so what we're using here is a large data set of vehicle registrations across the US. So this is county level vehicle registration. So all vehicle types by make, model, a number of other details for every county. And what I'm showing here is just a very simple visual of the results from 2012 to 2020. So we're using historical data from 2012 to 2020, looking at plug-in electric vehicles, so both battery electric and plug-in hybrid vehicles, and charging stations. So this is public charging stations available from the alternative fuel data center. And so what you can see here is we are getting kind of a clear relationship that as these, as charging stations go up, PEVs are going up. What we're interested in is which of these is sort of causing the other, and what's the strength of that relationship. Another sort of interesting visual on this is looking at PEV sales and then charging stations by state. And what this shows is that, yes, we get sort of this positive relationship between these 2 variables, but it's not perfectly linear. There's something else going on here. So you see Vermont has a lot of charging stations per capita. California, not nearly as many, but as a percent, I should say this is 2021 data, as a percent of vehicle sales, California has a higher percent. And so there's maybe other policies or other mechanisms at play here. And so, like I said, I'm going to sort of highlight those 2 because we'll come back to that later on how that can be interpreted in the final results that we get here. Something else that's interesting that we can look at in the data is that if you look at the percent of counties that have no vehicles or electric vehicles registered and no charging station, just over half of the counties in the US have neither of those. And then so if we filter those out so that we're filtering out anything that just has 0 through the whole time series, and then we plot the remaining data, you see that in 2012, about 80% of counties had neither PEVs or charging station. And then by 2020, within this data set that we know has data somewhere, by 2020, that's dropped down to 0. So this is the data set that we're going to use, which is about half of the counties in the US. So again, the counties that actually have some sort of meaningful data available to us. And so I'm going to look at 2 types of causality here, which are often called Rubin causality. And then the other one is often called Granger causality. I'm not a big fan of methods named after people because I think there's a lot of people that contribute to it. So I tend to refer to Granger causality as phasing causality because it's really sort of focused on the temporal phasing of 2 variables of interest. And then Rubin causality is potential outcomes because it's looking at the potential outcomes for a given different levels of treatment variable. And so what's very difficult about this in this case is in the typical phasing causality analysis in economics, you have a time series that has quite a few observations. What you're interested in is, do these 2 time series have a similar pattern, perhaps with some sort of temporal phasing? And so that's sort of the standard question in phasing causality. And then in potential outcomes, it's sort of the idea of, a classic example of this would be if you're looking at COVID and vaccinations, trying to measure what would be a person's outcome given that they were given the COVID vaccine and then given that they didn't have it. And obviously we can't both treat someone and not treat them, give them both the vaccine and not give them the vaccine. So the standard method of addressing that in observational data is to do a random control trial, which again, we can't do here because we can't sort of force people randomly to both have a vehicle and not have a vehicle. And so the challenge we have here is that we only have 5 years of data. So if you looked at this time series that I showed you for the United States, you see we have sort of 5 data points. Phasing causality really relies on a fairly large data set to really perform the analysis. Another challenge that we have with the standard Granger style causality test is that it relies on the data set being stationary, which basically just means that it's sort of not increasing or decreasing over time. It has this stationary pattern about some central point. And so we have neither of those features here. And that's sort of a bit of a challenge. And this is where I take off my econometrician hat and put on my engineer's hat and say, well, really, we don't really care if it's a time series or not. All we're really looking at is a pattern in the data set. And so what I do here is that I say, well, what if we take every county that we have data available for? So we have, I'm showing here sort of five counties and then the 5 years worth of data. And then what if we say, okay, we'll run this causality test. We're only going to look at 2020 data, so the last year of data. And then on top of that, we're only going to allow phases or time lags that are up to 5 years. So you can have sort of this whole data set that's, you can sort of think of it as a spatio-temporal time series, but we're only allowing legs up to 5 years. So that sort of allows us to use the full data set and look for these sorts of patterns. The other thing that we're going to do with this is that rather than using the traditional Granger causality tests, we're going to use several types of nonlinear Bayesian or Granger style causality tests running with a few different machine learning algorithms. And so, as I said, I'm sort of going to run it like this and say, well, only consider temporal lags that are less than 5 years, and then only consider the final years. And so what the results look like with that is given in this table. And essentially what I'm showing here is we run a few different styles of models. So an ARIMA, long short-term memory, multi-level perceptron, neural net. And what's shown here is just the results that are significant. These parameters are what are called Cohen effect sizes. Doesn't really matter too much what the numbers mean, but essentially what this is saying is that a larger, these numbers will lie somewhere between 0 and 1, and a larger number is going to denote a larger effect size. If it's bolded here, it's saying that it's statistically significant. And then if it's highlighted, then it's the largest value in each of these columns. And so then each of these columns is looking at assuming that charging stations phase sort of temporally cause PEV adoption, and then assuming that PEV adoption causes electric vehicle or a charging station. And then we're going to look at sort of 2-year lags in the first case, because we only have data for the EVs at 2-year lags, and then also looking at a 1-year lag. And essentially what we get out of this is it's entirely unclear from the data, at least with this initial analysis, which of these causes which. And so we don't have sort of clear evidence on that. I thought I was going to run fast, and I realized I'm running slow. So I'll go a little bit quicker through this. So as I said, I run 2 types of causal inference here. The first is this phasing. The second is a potential outcomes model. And here what I'm running is a propensity score matching algorithm. But because we have a continuous treatment, so the treatment variable here, I'm assuming, is charging stations. I run this nonlinear generalized additive model. And in that generalized propensity score function, I include state and year fixed effects, a spatial charging station lag, so do charging stations in adjacent counties affect outcomes in a given county, median household income, and then gas prices at the pump, because obviously that's going to affect EV adoption. And so what we get here is we get this positive causal relationship between charging stations and PEVs, and it sort of drops off at larger charging stations. So this is a non-linear, so we're not getting point estimates here. We get sort of a curve. And the interpretation of this at this point is really sort of going back to that California-Vermont comparison, where we're essentially finding that the states that have the highest charging stations per capita, maybe they're not doing enough sort of in other areas, and that, yes, it has this positive effect, but you really need to be looking at a few other factors too. And so the next sort of phases of this, some conclusions, is that there's no clear phasing, at least in this preliminary analysis, between adoption and charging stations. So there's likely some sort of a feedback relationship between them. As I said, charging stations aren't enough. We need other policies to increase adoption. As we saw, there's a significant zero inflation in the data set. The propensity score function I'm using right now is a linear one. Potentially, I could use a Tobit specification to account for some of those zeros, or a Bayesian additive regression tree, which Hill showed in 2011, could be useful in these sorts of continuous treatment and outcomes. And then also other control variables in that generalized propensity score function. And And on the topic of Tara's suggestion of papers being available, if you're interested in this work, and I also have another study with an undergrad on rural adoption, the full paper, which actually is an integration between the text and the code, is available on a GitHub page. So you can not only read the paper, you can run all of the code that you need to do all of the analysis and visualizations, and all the data sets are there. You can just sort of run the whole thing from beginning to end of what we've done here. So if anyone has any questions, I think we have about a minute here.
All right, Jason, we got quite a few notes in the chat box. Can you please take a look at it?
Yep.
Really, it's just the question I guess I have, if I can take over for a second, is just I'm not as familiar with the time series methods, and so I'm kind of confused why, if you have panel data, which it seems you do, you're not leveraging that information. The sort of
so the reason I'm not is actually just mostly a time constraint on my part. So I included, as I said, sort of as a fixed effect, but it's mostly just that I'm using a Python package for generalized propensity scores that I made I adapted some portions of it, but I essentially just have to update the likelihood function and the propensity score function to not be a linear regression, but have some sort of a REMA function, or like I said, I'm planning to update in various ways. But it's just that we only got the data set very recently. So I've sort of been working on this for about a month now. So it's in very early stages.
Gotcha. Because I agree, and I've reviewed a few papers that are trying to find out this link, like the chicken and egg, and it's just really hard to find an instrument, a policy that is truly exogenous on one of these fronts. And so it's really I sympathize with the problem.
Yeah, there's a paper by Lee and Chow in the Journal of Industrial Economics where they use grocery stores as an instrument to say where there's more grocery stores, they think that then they expect more charging stations, but not necessarily more battery electric vehicles. I'm not sure about that yet. But that's kind of the one paper that I've seen that's really seriously looked at this problem.
Well, great presentation, thank you. And yeah, I'll have to reach out to you.
All right, we have two more questions. Jesse, if you can take them very quickly.
Yeah.
Home chargers.
Oh, sorry, did you want me to answer them?
Yeah, I mean, how does this apply to the situation when we have many households, they have home chargers?
Yeah, that's a good question. So I think that's another reason why we see some of the results that we're seeing. So in another study that I have with an undergrad where we're looking at comparing rural versus urban effects, we do kind of find a variation where we sort of expect, we see that both low income urban areas of urban census tracts and rural census tracts have low percents of charging stations. But I think that it's more of an issue than in the low income urban areas, because like you're saying that in the rural area, they probably have home charging available versus in some of those low income urban areas, they potentially live in multifamily housing. And I know there's a study from CMU, I think about 6 years ago now, about the percent of households that don't have that they sort of estimate don't have access to home charging. which, as I recall, was a little bit higher than I expected. But there is definitely some, there is sort of a relationship.
All right. I mean, next question is about why not battery next to vehicles? Or you said it's
So I looked at both battery electric and plug-in hybrid electric. I'm just presenting the combination here, but that would be something interesting to sort of as a sensitivity test to run the models on both of those and see what the difference is. I'm not sure that the plug-in hybrid versus battery electric is going to have a big effect because both of them are relying on it, but I could see it having some slight effect. It would be interesting to look at to see if that's a big, large difference.
All right, thank you, Jason. We have to move on now. Our next speaker will be Mohamed Maliki, and he's from Iran originally, and he currently lives in Dallas, Texas, and he's a first-year PhD student civil environmental engineering at SMU in Texas. And he has a bachelor's degree, master's degree in urban regional planning, and his research lies in nexus of transportation planning health with a focus on microtransit services. All right, Mohamed, next 10 minutes is yours.
Thank you, Dr. Jun. Can you see my screen? Let me share my screen. Okay. Hello, everyone. I'll be presenting my work in progress titled A Framework for Measuring the Social Return on Investment of Microtransit Programs as a Solution to Eliminate Transportation-Related Barriers to Social Determinants of Health. This is a part of a bigger project which is funded by the National Academies of Science, Engineering, and Medicine Gulf Research Program that I'm working on with my colleague Miriam Zachem and our academic advisor, Dr. Janila Smith-Colin. To have a brief introduction, I'm going to start with social determinants of health, which refers to social factors that contribute to the health of people in a society and can range from access to healthcare facilities to access to jobs and access to healthy food. And many of the barriers to these determinants of health are caused by transportation, and thus creating programs to solve these barriers is an approach to improve the health of people. And as examples of this transportation intervention that can solve these barriers, we can mention on-demand microtransit programs that have been piloted nationally over the last decade in the US. And there are many examples of microtransit programs, many successful and cost-effective examples actually. And but for different contexts, it is still much need to be understood about the cost effectiveness of these programs in different contexts, for example, in rural areas, which is our case of a study. And because of that, we think an SROI or social return on investment is an approach that can evaluate or measure the returns from investing in such programs in different areas and measures the social values created by a funded activity in general. As it's already mentioned in the previous presentations, microtransit programs are multi-passenger IT-enabled transportation services that serves people through dynamically generated routes. In our case study, which is Holmes County in Mississippi, which is a rural county in a state which is often considered as the poorest state in the nation. There was the people there who have 11% of the people have ambulatory difficulty, and 42% of the population lives below 100% of the poverty level, and they are facing many barriers to social determinants of health. For example, they are facing barriers to access to healthcare, and there is no fixed route transit system in that area. And Because of that, they are having major problems on and on. And a free ride microtransit program was piloted in Holmes County during fall 2021 by an agency called Phoenix Mobility. And since it is a rural area and different from other cases of microtransit program, we need to understand how effective and how cost effective this program can be. And that's why we are trying to adopt an SROI to measure the effectiveness of this program. But in this paper, we follow every step that should be taken before the data collection part starts. And the aim of this paper is to first investigate the challenges and the feasibility of calculating SROI for this case. And also to do that, we conduct a review of basic methodologies and data available for calculating SROI. In order to do that, we review the characteristics of previously piloted microtransit program in the US, and also we review the existing literature on social return on investment to collect metrics and data and the challenges they have, and combine them all together to create, to first recommend performance measures for quantifying impacts, and then at the end we try to actually create a framework that supports SROI implementation for our case and helps us to implement SROI and measure the SROI for the case of microtransit programs. The research questions that we have here is that first we want to know what is SROI and what are the steps used to calculate SROI. Then we want to know what are the advantages and disadvantages of utilizing SROI for measuring and evaluating social values created by microtransit programs. And at the end, we want to know what are the characteristics of an SROI framework used for our context, which is measuring social return on investment of microtransit programs aiming to solve barriers to social determinants of health. SROI actually consists of 7 stages. In the first stage, the scope of the analysis needs to be established. And based on that, stakeholders need to be identified, because one of the challenges associated with social return on investment is that there are many stakeholders that can be involved in analysis, and this makes it difficult to measure all the negligible returns associated with the program. So based on the scope of the paper, only key stakeholders should be considered in analysis, and outcomes need to be mapped based on those, and the outcomes need to be monetized for an SROI, and impacts need to be established, and we can calculate the SROI and report the results based on those. Other challenges that are associated with SROI are that first, assumptions may need to be validated, and the large number of social returns that can be included in SROI is another challenge. And of course, costs of collecting and tracking data from different range of stakeholders is always challenging and expensive. In this part, you can see the framework that we designed for healthcare access. As I mentioned, there are different social determinants of health categories, and in this framework, we focus on the healthcare access part. In the blue flowchart, you can see the steps that we follow to identify a scope and map outcomes of the analysis. In the orange boxes, you can see the stakeholders that we included in our analysis. For example, Phoenix Mobility staff or the microtransit program staff are one of the stakeholders, and riders or medical clinic staff and community public are the stakeholders that are benefiting from the program. And on the blue, on the green boxes, you can see the metrics that we can use in our analysis, and the red boxes show the sources to collect those collect the data for those metrics from. And you can see that the right-hand side columns show the benefits and the left-hand side shows the service costs. And by comparing the benefits and costs, we can actually measure or report the results of the SROI analysis. As I mentioned, this is the last step before the data collection part, and this framework can actually contribute to the existing knowledge of SROI as an approach for measuring the SROI of solution as microtransit programs, which are aiming to solve transportation-related barriers to social determinants of health. And it can help decision makers want to adopt SROI for different cases of microtransit programs or transportation interventions. And for the future work that we are actually working on right now, we are trying to create frameworks for other social determinants of health, such as job access and access to food. And we try to combine them all together to measure the return on investment for our social determinants of health. And thank you everyone for your attention, and I will welcome all the questions that you might have.
Thank you, Mohamed. Thank you for the presentation, and we are right on time. And we do have a few minutes for questions for Mohamed. Any questions? No questions? Okay, so this is about the social return of the investment, right? Well, it's just, I'm a data person. I mean, sometimes I will say, okay, do we have data ready to quantify the returns of investments? Do you have any suggestions for us to get the data to quantify the social return?
But could you please repeat the first part of your question?
Oh, I was just saying I'm a data person. I always looking for data to quantify the whatever the benefits, the benefits or impact of any investments or deployments. But for this type of social return, how do we quantify the social return? Or by rating people's perceptions?
Well, this is the most, I would say, the most challenging part in social return on investment. Actually, SROI works through monetized values. So when we map the outcomes and map the benefits, we actually need to monetize them. So we can review the other resources that, for example, we have this social benefit, which is increased leisure time because of reduced travel time. And we have to just realize how much it can reduce SRS of people and how it can affect the wellness of people. And based on that, we can monetize. And we see that if people have increased leisure time, what other medical costs will decrease. For example, their medical costs to visit therapists will decrease, and we need to monetize based on that. And we have monetized values and we measure them. And at the end, when we compare, it is, we can, this is the only when we can compare the results. But they are mostly based on assumptions.
All right, thank you. Thank you. We need to move on. Our last speaker who is unable to join us today, but we have his recording. And now, please, Zoning, please play his recording so we can all watch together.
Okay, can you guys see the video?
Yes.
Okay, I will start to play.
Hello everyone, my name is Dong Zhaojin from Michigan Tech University. My topic today is about the distinguishing of the wide-based air truck in Michigan by the convolutional neural network. And my advisor is Dr. Zhanping Yu. The content consists of 3 parts. First is the introduction, second is the research work descriptions, the third is ongoing work. First, we are going to the introduction first. That is, what is the wide-based head? Like the picture shown here, the wide-based head means the tail that has a wider compact area compared with the standard tail size, and it will help to increase the load carrying capabilities. And dual-tailed is we call the dual-tailed semblance. It's a typical tail that used for the conventional truck. And this research work is sponsored and supported by the Michigan Department of Transportation. And so why the wide base tail is a valuable topic is because as the American Truck Association reported that there is a significant potential for the fuel savings, and also these benefits will let the truck industry from using the wide base tail, and also they think the market will increase the usage in the future of the wide base tail. So the objective of this study is to investigate the usage of the wide base tail in Michigan, and the convolution neural network method will be applied to help to distinguish the wide base tailed truck. And next we go to the research work descriptions. First is collect the data for the wide base tailed truck. We just check some open source dataset like the ImageNet and K410 and Cargos. I found they have some datasets to compare the car and the truck. But actually, I do not find there have the specific annotation dataset with different truck classes and also the wide base tailed truck. And also we have checked the video system from MDOT, and I like the picture shown here. All the videos we check the online videos, it's unclearly to see the truck class and also the truck tailed types. So we have to collect data by ourselves. And in order to get the data, we contact the Michigan State Police weigh station and also the Michigan DOTs to obtain the permit to get the pictures and the videos in the weigh stations to obtain the valuable dataset. And also I have to mention in the weigh stations, they can only obtain the truck types and also the truck weight. The cost of the weigh station is very expensive, and also it cannot be used in other places after construction. So the wide base tailed usage condition cannot be directly obtained by the weigh station. So we have to obtain by ourselves. So we check the traffic volume map in Michigan and the weigh station distribution map in Michigan. We finally select 5 weigh stations and the top 5 traffic volume from New Buffalo weigh stations, Erie weigh stations, Grass Lake weigh stations, Blue Valley weigh stations, and Coldwater weigh stations. And we take the GoPro there and take the videos and get the data. And this is the summary data we get. Like the left page, like the picture showing that the total percentage of the truck with wide base tail is about 9.7% to 12.9%. The average value is about 10.87%. And on the right shows the daily truck numbers. And the maximum is the New Buffalo truck, and also the Oro or Eric weigh station also has the high traffic value. Totally, we get about 6,000 truck data at that days, and also we just figure out the within the truck if there any wide base tail distribution on the truck. We found that the drive anchors and the back trailer anchors have the higher likelihood of the usage of wide base tail. And also here we introduce the FHWA's, the Federal Highway Administration vehicle classifications. So actually the truck we focus on is from class 4 to class 13. Actually, when we come to the weigh stations, we found the truck with wide base tail is mainly focused on class 9, class 10, even some in class 13. And the work we did after we get the picture is we did the image augmentations. Like the image, we totally increase the data set we have from the original picture, get the RGB shift, and the green pictures, and random shallows, and the rainings, and channel shuffle, and the random sunshine, and also the mirror pictures. And we based on the reference paper to do this work, and we can increase the data set. And for the picture distinguish, we tried is the AlexNet model, and we got this picture is get from the source like shown below. AlexNet is the contents of eight layers. The first 5 layers is convolutional layers, and some of them is followed by the max pooling layers, and the last 3 layers is for connect layers. So we use this network to get the models and distinguish the pictures. And also we also develop a app based on MATLAB, like the picture shown here. We can load the CN models and load the untrained model pictures. We get random on the road, and also we can run the model. We can get the results quick if what class truck it is, and also if the truck is a wide-based tailed truck or not. And also for the modeling work, we just use the 70% of image for training and left 30% image for validations. And after the parameter optimizations, the accuracy can reach up to 95%. So it can get a very promising and good results to distinguish the picture of the truck tailed type and also the truck class. So after that, we found that if we can get the picture, but it's hard to get automatically get the number of the truck and also the usage conditions. So we want to develop another CN method we call the Euro V4 and deep sort method to help to distinguish the wide-based tailed truck. The Euro V4 is a one-stage objective detection models developed from Euro V3s, and this is a structure generally we use from I get from the paper shown below, and shown the main step of the Euro V4 include the input layer, backbone, neck, and dense prediction. And in this page, just shows the basic structure of the deep sort is called the simple online and real-time tracking with deep associations metric, and we get the reference. We get it from the reference GitHub code, and also in order to do the trainings, we annotation about more than 6,000 pictures from way station, and we use the library image from the reference and get the annotation pictures and training in the Euro models. And here is the ongoing work, and we can get the results from the Euro and deep sort method, but actually it's not as good as we wished, because the results is still not as so accurate as we wanted. So I will need to do more parameter optimizations and also collect more data sets to improve the accuracy of the models. And also we hope after we trainings it can help to detect the truck tail type and also the truck types in way station in Michigan. And also we hope the error rate from the truck type and the tail type maybe cannot as accuracy as human performance zones, but similar performance. So that's all. Thank you.
All right, then I think that's all we have.